Lesson Overview. When you are planning storage, you need to determine how your servers will access disks. In some cases, you can attach disks directly to the servers that require the storage. However, in enterprises, storage often is in NAS or SANs, which provide more flexibility. In this lesson, you will learn about the different methods that you can use to provide servers with storage access. Objectives. After completing this lesson, you will be able to describe the storage solutions that are deployed in your environment.
Describe das.
On describe nas.
Au describe sans.
You identify when you should use different storage types. You list differences between block-level storage and file-level storage. Organizations have a wide variety of storage options, such as DS, NAS, and SANs. Each of these options is valid for different scenarios. Almost all servers provide built-in storage or direct attached storage, DS. DOS can include disks that are physically located inside the server or that connect directly with an external array, or disks that connect to the server with a USB cable or an alternative connector. However, because you connect DS storage to the server physically, the storage is unavailable if the server fails. DOS comes in various disk types, such as serial ATA, SATA, serial attached SCSI, SAS, or solid-state drive, SSD. These disk types all offer different speeds and performance levels and have advantages and disadvantages. Advantages of using DS. A typical DS system has a data storage device that includes a number of hard drives, which connect directly to a computer through a host bus adapter, HBA. There are no network devices, hubs, switches, or routers between the DS and the computer, but rather, the storage connects directly to the server that utilizes it. Therefore, DES is the easiest storage system to deploy and maintain. DOS typically is the least expensive storage that is available, and it is available widely in various speeds and sizes to accommodate different installations. Additionally, it is inexpensive and is very easy to configure. In most instances, you simply plug in the device, ensure that the running Windows operating system recognizes it, and then use the disk management feature to configure the disks. Disadvantages of using DS. Storing data locally on DS makes data centralization more difficult because the data is on multiple servers. This might make it more complex to back up data, and users might find it more difficult to locate the data that they want to find. Furthermore, if any one device to which DS connects suffers a power outage, the storage on that device becomes unavailable. With DS, allocating additional storage to servers can be more complex than with a SAN. With DS, a physical disk needs to be installed in the server, whereas with a SAN, existing unallocated storage can be given to a server to expand storage without physically accessing the server. NAS is storage that connects to a dedicated storage device and is then accessed over the network. NAS differs from DAS because the storage does not attach directly to each individual server, but rather is accessible across a network to many servers. NAS has two distinct solutions: a low-end appliance, NAS only, and an enterprise-class NAS that integrates with a SAN. Each NAS device has a dedicated operating system that solely controls data access on that device, which reduces the overhead associated with sharing the storage device with other server services. Windows Storage Server, a feature of Windows Server, is an example of NAS software. NAS devices typically provide file-level access to storage, which means that data in the storage is accessible only as files and folders, and you must use protocols such as Common Internet File System, CIFS, Server Message Block, SMB, or Network File System, NFS, to access the files. To enable NAS, you need a storage device. Frequently, these devices do not have any server interfaces, such as keyboards, mice, and monitors. To configure the device, you need to provide a network configuration and then access the device across a network. You then can create shared folders on the device by using the name of the NAS and the share that you create. These shares then are accessible to the network's users. Advantages of using NAS. NAS is an ideal choice for organizations that are looking for a simple and cost-effective way to achieve fast data access at the file level for multiple clients. NAS users benefit from performance and productivity gains because a NAS device's processing power is dedicated solely to file distribution. NAS also fits nicely into the market as a mid-price solution. It is not expensive, but it suits more needs than DAS in the following ways. NAS storage typically is much larger than DS. NAS typically includes redundant array of independent disks, RAID, for data redundancy. NAS offers a single location for all critical files, rather than dispersing them on various servers by using DS. NAS offers centralized storage at an affordable price. NAS units are accessible from any operating system. They often have multiple protocol support and can serve up data via CIFS and NFS simultaneously. For example, Windows and Linux hosts can access a NAS unit simultaneously. NAS also is a plug-and-play (PNP) solution that is easy to install, deploy, and manage, regardless of whether you have IT staff on site. Disadvantages of using NAS. NAS is slower than SAN technologies. You typically access NAS by using Ethernet protocols, and it relies heavily on the network that is supporting the NAS solution. Therefore, NAS commonly is used as a file-sharing/storage solution, but you cannot and should not try to use it with data-intensive programs such as Microsoft Exchange Server and Microsoft SQL Server. NAS is affordable for small to mid-sized businesses, but provides less performance and might be less reliable than a SAN. For this reason, most large enterprises use SANs rather than NAS. The third type of storage is a SAN, which is a high-speed network that connects computer systems or host servers to high-performance storage subsystems. A SAN usually includes various components such as HBAs, special switches to help route traffic, and storage disk arrays with logical unit numbers, LUNs, for storage. A SAN enables multiple servers to access a storage pool in which any server potentially can access any storage unit. However, because a SAN uses a network, you can use it to connect many different devices and hosts, and to provide access to any connected device from almost anywhere. SANs provide block-level access. This means that rather than using a file access protocol to access disk contents as files, SANs write blocks of data directly to the disks by using protocols such as Fibre Channel over Ethernet or Internet SCSI, ISCSI. Today, most SAN solutions offer SAN and NAS together. The backend head units, disks, and technologies are identical, and the access method is the only thing that changes. Enterprises often provision block storage from the SAN to the servers by using Fibre Channel over Ethernet or ISCSI, while NAS services typically are available through CIFS and NFS. Advantages of using SAN. SAN technologies read and write at block levels, which makes data access much faster. For example, with most DS and NAS solutions, if you write a file of 8 GB, GB, the entire file has to be read/written and its checksum calculated. However, with a SAN, the file is written to the disk based on the block size for which you configure the SAN. This speed is accomplished by using Fibre Channel and block-level writing, instead of reading/writing an entire file by using a checksum. SANs also provide centralization of storage into a single pool, which enables storage resources and server resources to grow independently. They also enable dynamic storage assignment from the pool when necessary. You can increase or decrease storage on a given server as necessary, without complex reconfiguration or recabling of devices. You have a common infrastructure for attaching storage, which enables a single common management model for configuration and deployment. Storage devices that multiple systems share inherently. Data transfer directly from device to device without server intervention. You have a high level of redundancy. You deploy most SANs through a network with multiple network devices and paths. Additionally, the storage device contains redundant components, such as power supplies and hard drives. Disadvantages of using SAN. The main drawback to SAN technology is that you likely will need to use management tools and have expert skills because of its configuration complexities. Additionally, it is considerably more expensive than DS or NAS. An entry-level SAN often costs as much as a fully loaded server with a DS or NAS device, and that is without any SAN disks or configuration. To manage a SAN, you must have a firm understanding of the underlying technology, including the LUN setup, the Fibre Channel network, the block sizing, and other factors. Additionally, each storage vendor often implements SANs by using different tools and features. Therefore, organizations often dedicate personnel to SAN deployment solely. Note, you can implement SANs by using a variety of technologies, and the most common options are Fibre Channel and ISCSI. A good understanding of DS, NAS, and SAN is the first step you must take in identifying the storage solution that best fits your requirements, and you should be aware that each of these storage technologies has expanded its available features and added flexibility. Often, you will not have a clear best choice, so this next topic examines the three topologies again, and compares them and explains which is the best solution for different scenarios.
DAS.
You might consider using DS because it typically is the least expensive and least complex solution. However, DS might require more administrative overhead than NAS and SAN, especially if you deploy multiple DS solutions. For example, imagine that your organization is deploying 15 Microsoft Hyper-V nodes in a failover cluster in Windows Server. If you use NAS or SAN, a single highly available storage solution can accommodate the failover cluster. However, if you use DS, you might need 15 appliances. In such cases, DS can create storage sprawl, which means that there are ever-increasing and expanding storage islands, which might be difficult to manage and maintain. To combat this, the latest DS solutions sometimes include some key SAN features, including multiple communication protocols, enterprise management software, and easy expansion. You can use these features to add additional disk shelves. Entry-level DS offerings provide only a single shelf in each appliance and do not support expansion. These restrictions lead to storage sprawl. However, with high-end DS systems, you can expand the disk shelves and disk count and deploy solutions easily with hundreds of terabytes, TBs, of storage space. Therefore, these solutions can handle the Hyper-V failover cluster scenario that the prior section describes. In larger organizations, some database management teams and messaging teams prefer to use DS solutions to reduce their reliance on the organization's storage team. This gives them more control over their own storage. Thus, a large majority of organizations use NAS, although many do not refer to their shared folder solutions as NAS. Third-party storage companies have introduced or expanded their NAS offerings, so it is common for SAN solutions to deliver NAS services via CIFS or NFS as well. Therefore, in many organizations, SAN and NAS often share the same storage appliances, disk shelves, and supporting infrastructure. NAS is so ubiquitous that it likely is not useful to compare it directly to DS or SAN. DOS and SAN often compete directly with each other, but NAS typically plays a complementary role in systems that also incorporate DS and SAN. Recently, some technologies have adopted support for NAS. One such example is Hyper-V, which now supports storing virtual machines on SMB 3.0 shares. If additional technologies begin to support NAS, then more direct competition with DS and SAN is likely in the future. SAN solutions are known widely as the best enterprise storage solution. For a long time, SAN was the only solution for high-performance storage. Not only is it flexible and high-performing, but you also can expand it more easily than DS and NAS. However, DS and NAS have expanded their markets recently. DOS solutions can offer high-performance storage without the complexity of a SAN because it utilizes the latest disk and SSD technologies. Countering that, SAN solutions can offer the same disk and SSD technologies on a much larger scale, and the scale is the key differentiator. Whereas the largest DS solutions offer hundreds of TBs of storage space, the top SAN solutions offer thousands of TBs of storage space. Additionally, SAN solutions offer more spindles, which often lead to better performance. Finally, SAN solutions offer the best management tools. SAN management tools often provide a single management interface. The most enterprise features. For example, a common feature is an SSD cache in front of a huge spindle of spinning disks. The most flexibility. SANs provide SAN and NAS services in a single solution. Future trends. With each new version of Windows Server, Microsoft is making Windows Server with DS a more competitive option compared with SAN storage. Windows Server 2012 introduced storage spaces to provide redundancy for DS without requiring a RAID controller. However, we recommend that you use caching controller for performance. Windows Server 2012 R2 introduced storage tiering to allow the most frequently accessed disk blocks to be automatically stored on SSD drives instead of spinning disks. High availability for shared folders was also available by implementing Scale-Out File Server. Windows Server also adds storage replica to provide block-level synchronous or asynchronous replication between two servers that are using DS. The storage features that Windows Server includes are expanding steadily to include those available only in SANs previously. Using Windows Server with DS is often much less expensive than using it with a SAN if the feature set meets your needs. Scenarios for using DS, NAS, or SAN. The following table highlights some common storage scenarios and describes the capabilities of DS, NAS, and SAN in each scenario.
Cenário das nação.
High-performance storage for transactional databases, very good performance, and the lowest cost solution, not a valid solution for most database servers. Excellent performance and features make this the best choice for transactional databases. Might add significant administrative overhead in large enterprise environments. User home folders, very good performance, but might expand into decentralized islands of storage. Best fit for user home folders because it offers CIFS access from any computing device without prohibitive costs. Excellent performance and features, but more than required for user home folders. Enterprise management of many DS installations adds administrative overhead. Home folders might need to be centralized. Might be cost prohibitive. Storage of virtual machines, very good performance, but the administrative overhead is higher than SAN solutions supported for Hyper-V in Windows Server 2012, R2 or later. NAS is a good choice when trying to keep costs and complexity low. Excellent performance and features make this the best choice for most virtual environments. Branch Office shared folders, easy to deploy and at a low cost. Easy to deploy, often cost prohibitive and more features than what is required for a branch office. Often the best choice for general shared folders and branch offices because you do not need infrastructure at the branch offices. Moderate cost. Often a good choice for branch offices that have a small infrastructure on site. Tiered storage for applications not as flexible as SAN, but viable for a small budget situation. Limited communication protocols compared to SAN, but some solutions are viable, such as a scale-out file server with storage spaces and tiering most flexible. Built-in tiering, caching, and other performance enhancements make SAN the best choice for applications. Microsoft Exchange database and log storage, lowest cost, very good performance, and a very good alternative to SANs, especially for messaging teams that prefer to administer their own storage. Not a valid choice. Excellent performance and features make this a top choice. You can arrange data on a disk in two ways, by blocks or by files. These ways of arranging data are block-level storage and file-level storage. Often, one arrangement or the other is the best solution in a particular scenario. Sometimes, however, they complement each other in a storage infrastructure. For example, it is common to use both types of storage in large enterprise environments. You typically use block-level storage in conjunction with a SAN, and part or all of that storage is allocated to servers. You typically use file-level storage in conjunction with NAS, and NAS, a storage server or a file server allocates those chunks of storage by using file-level protocols, such as CIFS or NFS. Additionally, you typically place file-level storage on block-level storage. Block-level storage. Block-level storage is delivered to servers via a SAN, most often by using one of the SAN communication protocols, such as ISCSI, Fibre Channel, or Fibre Channel over Ethernet. Storage administrators create storage volumes out of chunks of block-level storage. Inside the volumes, storage administrators create LUNs, which are virtual storage areas. You configure or present LUNs for use on one or more servers. Servers see the presented LUNs as physical hard drives, and administrators create volumes in Windows Server based on the LUNs. Volumes are formatted with a file system, such as the NTFS file system or Resilient File System, REFS, and then accessed in the same manner as a physical or virtual hard disk. Block-level storage has the following characteristics. It is very flexible. For example, you can use it as an operating system volume, a data volume, or a storage location for shared folders. It is not tied to a specific operating system or a specific file system. All core operating systems and file systems support it. Operating systems can start from block-level storage LUNs. This means that your organization can deploy diskless physical servers. In such a scenario, the servers use Fibre Channel or ISCSI HBAs to connect to their boot LUN upon startup. You can present block-level storage directly to virtual machines to meet high-performance storage needs. In Hyper-V, you can present block-level storage to virtual machines by using a pass-through disk or by using virtual fiber channel. File-level storage. CIFS and NFS are the primary communication protocols that file-level storage uses. CIFS originally was an enhanced version of SMB. Today, however, the terms CIFS and SMB often are used interchangeably. Microsoft continues to make enhancements to CIFS with many major releases of the Windows Server operating system. File-level storage has the following characteristics. The access to file-level storage occurs over file-sharing protocols only. File-level storage sits on top of block-level storage and has a file system. Some applications support file-level storage, but others do not. In Windows Server 2012 R2, Hyper-V began supporting virtual machine storage in SMB 3.0 shared folders. File-level storage often is more economical than block-level storage. Lesson overview. You can use multiple protocols to configure SANs, and the protocol that you select for a SAN typically is based on your organization's needs and the skills of your technical staff. Fiber channel is the best performing solution for SANs, but it is the most complex and expensive system to implement. An ISCSI SAN is less expensive because the equipment is less specialized and is simpler to implement and manage. In this lesson, you will learn about fiber channel and ISCSI. Objectives. After completing this lesson, you will be able to describe fiber channel, list considerations for implementing fiber channel, describe ISCSI, identify components that are part of an ISCSI SAN, list considerations for implementing ISCSI, describe physical storage components, configure an ISCSI target. Fiber channel is a high-performance network technology that you use primarily to connect computers to SANs. It is a standard with a long history, and it was approved in 1994. Fiber channel relies on the fiber channel protocol that transports SCSI commands over a network. A typical fiber channel implementation contains the following components. SAN. In a fiber channel implementation, SAN is the storage backend. It serves as a fiber channel target, which is the component that listens for requests from computers. A computer with an HBA card. In a fiber channel implementation, a computer with an HBA card is an initiator because it initiates requests when it needs to access data on the SAN. A fiber channel switch. In a fiber channel implementation, you typically use fiber channel switches so that computers do not connect directly to a SAN. SANs often have a very limited number of target ports, and those ports almost always connect to fiber channel switches. Fiber channel over Ethernet is a newer implementation of fiber channel over a standard Ethernet network. It is becoming more popular because it offers outstanding performance, particularly when you use it over your inexpensive and often pre-existing Ethernet infrastructure. You can use fiber channel over Ethernet to converge all of your company's disparate communication mechanisms to Ethernet. There are three main advantages to using fiber channel over Ethernet to merge your communication systems, including that it is easier to manage a single network topology than a complex multi-type network. You can use many of the standard network troubleshooting tools with fiber channel over Ethernet. Specialized training typically is not required. You can arrange a fiber channel network in one of three layouts. Arbitrated loop. In an arbitrated loop, fiber channel hosts and storage devices connect in a ring, and you do not need switches. This option was an inexpensive way to begin using fiber channel when it was first introduced. However, it is quite rare today because fiber channel and converged switches are very affordable. Point-to-point. In a point-to-point deployment, a fiber channel host connects directly to a storage device, and you do not need switches. However, organizations rarely use this option because a very limited number of ports are available on storage devices. Switched fabric. This is the most common fiber channel deployment. Switched fabric environments use fiber channel switches. All fiber channel hosts connect to fiber channel switches, and the fiber channel switches connect to the backend storage. You must consider several important factors when you decide whether to use fiber channel in a storage environment, including infrastructure requirements, storage bandwidth requirements, connectivity reliability and security, asset and administrative costs. Infrastructure. The infrastructure requirements of Fibre Channel are often extensive for new storage deployments. When you use Fibre Channel, you typically install a specific and separate infrastructure for it. This dedicated infrastructure includes the following components: fabric or network switches. In a network that uses only fiber optic cables, you might use Fibre Channel switches. However, many networks use more than one type of cable, and you might combine separate networks that each are using a different type of cable. In these converged networks, switches must be able to handle multiple types of traffic and cables. HBAs. An HBA is an add-on card or functionality that is built into a computer's motherboard to enable communication over a Fibre Channel or Ethernet network. The additional cabling. Cabling is a critical component, and it typically consists of fiber optic or Ethernet cabling. Storage controllers. Storage controllers, or storage heads, manage communication to the back-end storage. A new Fibre Channel infrastructure typically requires switches that are dedicated solely to the storage environment. A dedicated network often provides better performance and security because the switches are only for storage-related traffic to and from the hosts and storage controllers. Fabric switches also generally require additional small form factor pluggable transceivers that support Fibre Channel cabling. This increases the infrastructure's initial cost. Additionally, each host also requires at least one dedicated HBA and often two HBAs for redundancy, which you must manage and cable separately from your production network traffic. Finally, the storage system that you are using also must support Fibre Channel. You can use Fibre Channel with several cable types, the most common of which are single-mode fiber optic, multi-mode fiber optic, Ethernet, O-Fibre Channel over Ethernet, O-Fibre Channel over IP, Ethernet over copper. Dedicated Fibre Channel infrastructure uses fiber optic cabling in a variety of standards. Multi-mode fiber optic cabling is cheaper than single-mode fiber optic cabling and is suitable for most data centers. The 128 gigabits per second (Gbps) standard for Fibre Channel supports multi-mode fiber at up to 100 meters and single-mode fiber at up to 2,000 meters. Most organizations have no need for a 2,000-meter distance, but when required, single-mode fiber provides the option. Bandwidth. One of the most important benefits of using Fibre Channel to connect to a storage environment is the bandwidth and reliability that Fibre Channel can deliver. Currently, with bandwidth speeds up to 16 Gbps per port, Fibre Channel outperforms Ethernet on a per-port basis. This additional performance capability can be a major factor in deciding whether to use Fibre Channel. The most recent Fibre Channel standard is 32 gigabits per second. Reliability and security. Fibre Channel provides good connectivity, reliability, and security, which are all important benefits. The Fibre Channel protocol is superior to the Ethernet protocol because it requires that frames are received in a specific order. This is not the case with Transmission Control Protocol, TCP-based protocols, which can degrade performance and reliability. Additionally, because Fibre Channel deployments typically use a dedicated infrastructure, it is more secure and less susceptible to attack or degradation. In contrast to Fibre Channel, if a system's storage communication is shared with other network traffic, the storage operations of a host are vulnerable to the same attacks that can disrupt TCP communication. For example, a distributed denial of service (DDoS) attack in an environment with a converged infrastructure might prevent both TCP and storage communication. When you use a dedicated Fibre Channel infrastructure, this vulnerability is minimized. A middle ground in this scenario could be Fibre Channel over Ethernet, which provides the reliability of Fibre Channel over a typical Ethernet network. Costs. The personnel that manage the Fibre Channel solution require a specialized set of skills, which can make it more expensive than other storage solutions. In-house personnel might need additional training to initially deploy and manage the solution, as well as ongoing training to stay current as the technology changes. If you use a third-party vendor to support your Fibre Channel solution, your costs might be the same or even higher than if you use your organization's staff. ISCSI is a protocol that supports access to remote, SCSI-based storage devices over a Transmission Control Protocol/Internet Protocol (TCP/IP) network. ISCSI carries standard SCSI commands over IP networks to facilitate data transfers and to manage storage over long distances. You can use ISCSI to transmit data over local area networks, LANs, wide area networks, WANs, and intranet, or the Internet. ISCSI relies on standard Ethernet networking architecture. You optionally can use specialized hardware, such as an HBA or network switches. ISCSI uses TCP, IP, and specifically TCP port 3260. This means that ISCSI enables two hosts to negotiate and exchange SCSI commands by using an existing Ethernet network. Examples of what the two hosts negotiate include session establishment, flow control, and packet size. By doing this, ISCSI takes a popular, high-performance, local storage bus subsystem architecture and emulates it over networks, thereby creating a SAN. Unlike some SAN protocols, ISCSI requires no specialized cabling. You can run it over an existing switching and IP infrastructure. However, to ensure performance, you should operate an ISCSI SAN deployment on a dedicated network. Otherwise, you might experience severely decreased performance. An ISCSI SAN deployment includes the following: IP network. You can use standard network interface adapters and standard Ethernet protocol network switches to connect servers to a storage device. To provide sufficient performance, the network should provide speeds of at least 1 gigabit per second and should provide multiple paths to the ISCSI target. We recommend that you use a dedicated physical and logical network to achieve fast, reliable throughput. ISCSI targets. ISCSI targets present or advertised storage, similar to controllers for hard drives of locally attached storage. However, servers access this storage over a network, rather than accessing it locally. Many storage vendors implement hardware-level ISCSI targets as part of their storage device's hardware. Other devices or appliances, such as Windows storage server devices, implement ISCSI targets by using a software driver and at least one Ethernet adapter. Windows Server provides the ISCSI target server, which is a driver for the ISCSI protocol, as a role service of the file and storage services role. ISCSI initiators. The ISCSI target displays storage to the ISCSI initiator or client. The ISCSI initiator acts as a local disk controller for the remote disks. All Windows versions since Windows Server 2008 and Windows Vista include the ISCSI initiator and can connect to ISCSI targets. ISCSI qualified name, IQN. IQNs are unique identifiers that ISCSI uses to address initiators and targets on an ISCSI network. When you configure an ISCSI target, you must configure the IQN for the ISCSI initiators that will connect to the target. ISCSI initiators also use IQNs to connect to ISCSI targets. However, if name resolution on the ISCSI network is a possible issue, you can identify ISCSI endpoints, both target and initiator, by their IP addresses. This topic discusses the two main components of ISCSI, an ISCSI target server and an ISCSI initiator. ISCSI target server. The ISCSI target server role service provides for a software-based and hardware-independent ISCSI disk subsystem. You can use the ISCSI target server to create ISCSI targets and ISCSI virtual disks, and then use the server manager to manage these ISCSI targets and virtual disks. The ISCSI target server that Windows Server includes provides the following functionality: network or diskless boot. You can deploy diskless servers rapidly by using boot-capable network adapters or a software loader, and you can save as much as 90% of the storage space that you use for operating system images by using differencing virtual hard disks. This is ideal for large deployments of identical operating system images, such as on virtual machines that are running Hyper-V or in high-performance computing (HPC) clusters. Server application storage. Some applications, such as Microsoft Exchange Server, require block storage. The ISCSI target server can provide these applications with continuously available block storage. However, because the storage is accessible remotely, it also can combine block storage for central or branch office locations. Heterogeneous storage. ISCSI target server supports ISCSI initiators that are not running Windows, so you can share storage on servers that are running Windows in mixed environments. Collab environments. The ISCSI target server role enables your Windows Server computer to be a network-accessible block storage device. This is useful if you want to test applications before deploying them on SAN storage. The features of the ISCSI target server in Windows Server include authentication. You can enable Challenge Handshake Authentication Protocol, CHAP, to authenticate initiator connections, or enable Reverse CHAP to allow the initiator to authenticate the ISCSI target. Query Initiator Computer for ID. To use this, you must use Windows 8 or Windows Server 2012 and newer operating systems. Virtual Hard Disk Support. You create ISCSI virtual disks as virtual hard disks. Windows Server supports both .vhd and .vhdx files, and .vhdx supports up to 64 terabytes capacity. You create new ISCSI virtual disks as .vhdx files, but you can import .vhd files. Scalability. The maximum number of ISCSI targets per target server is 256, and the maximum number of virtual hard disks per target server is 512. Additional reading. For more information, refer to ISCSI target server scalability limits. http://aka.ms/dfxgja. Manageability. You manage the ISCSI target server by using Server Manager or Windows PowerShell. Windows Server uses the Storage Management Initiative Specification Provider with Microsoft System Center 2012 Virtual Machine Manager and later versions to manage an ISCSI target server in a hosted and private cloud. You could use the following Windows PowerShell templates to manage the ISCSI target server. Install Windows feature FSISCSI target server. New ISCSI virtual disk /ISCSI virtual hard disk /1. VHDX, size 1 GB. New ISCSI server target SQL target, initiator IDs IQN. ICN.1991, 05.com. Microsoft, SQL1.adatum.com. Add ISCSI virtual disk target mapping SQL target /ISCSI virtual hard disk /1. VHDX. Additional reading. For more information, refer to ISCSI target templates in Windows PowerShell. http://aka.ms/j1iomo. When you enable the ISCSI target server to provide block storage, the ISCSI target server capitalizes on your existing Ethernet network. You need a dedicated network for ISCSI to ensure performance, or you can use quality of service (QoS) standards on your existing network. If high availability is important to your organization, you should configure a high availability cluster. However, when you configure a high availability cluster, you will need shared storage for the cluster. This storage can be hardware fiber channel storage or a serial attached SCSI storage array. You configure the ISCSI target server as a cluster role in the failover cluster. Windows Server introduces the Storage Spaces Direct feature, which uses unshared storage to make a high availability cluster. It does this by using only local unshared storage and commodity hardware. ISCSI Initiator. The ISCSI Initiator was introduced in Windows Server 2008 and Windows Vista, and it is installed by default. To connect your computer to an ISCSI target, you must start and configure the service. You could use the following Windows PowerShell templates to manage your ISCSI Initiator. Start service from SysI. Set service from SysI. Startup type, automatic. New ISCSI target portal address ISCSI server 1. Connect ISCSI target, node address ICN.1991, 05.com. Microsoft, NetBoot, 1, SQL target. Before embarking on an ISCSI deployment, you should look at your infrastructure, staff, and customer requirements to ensure that you select the appropriate solution. The following are the primary considerations that you should take into account. Network speed and performance. The network speed should be at least 1 gigabit per second, but in many cases, ISCSI networks in a data center now are 10 gigabits per second, 40 gigabits per second, or even 100 gigabits per second. High availability. The network infrastructure must be highly available because data is sent from the servers to the ISCSI storage over network devices and components. Security. The ISCSI solution should have an appropriate level of security. In situations where you need high security, you can use a dedicated network and ISCSI authentication. In situations with lower security requirements, you might not have to use a dedicated network and ISCSI authentication. A vendor information. Read the vendor-specific recommendations for different types of deployments and applications that use ISCSI storage, such as Exchange Server and SQL Server. Infrastructure staff. IT personnel who will design, configure, and administer the ISCSI storage must include IT administrators with different areas of specialization, such as Windows Server administrators, network administrators, storage administrators, and security administrators. This will help you design an ISCSI storage solution that has optimal performance and security. It also will help you create consistent management and operations procedures. Application teams. The design team for an ISCSI storage solution should include application-specific administrators, such as Exchange Server administrators and SQL Server administrators, so that you can implement the optimal configuration for the specific technology or solution. In addition to looking at the infrastructure and teams, you also need to investigate competitive solutions to see if they better meet your business requirements. The primary ISCSI competitors are Fibre Channel over Ethernet, and InfiniBand. In a storage infrastructure, several types of adapters and controllers comprise a storage system's physical foundation, including network adapters, HBAs, converged network adapters, InfiniBand host channel adapters, disk controllers. This topic examines the characteristics of these components and provides a high-level overview of scenarios for which each component is best suited. Network adapters. Network adapters are composed of microchips and physical ports that are on a motherboard or an expansion card. Network adapters provide connectivity primarily to Ethernet networks. Network adapters communicate over a wired network by using an RJ45 port or over wireless networks by using the 802.11 wireless network standard. Network adapters are the most cost-effective storage connectivity solution. Current network adapters operate at up to 100 Gbps per port, although 10 gigabits per second and 40 Gbps are more common. You can configure teaming to achieve performance, failover, or both. When you use teaming, all network adapters that are part of a team combine to create a virtual network adapter, or team network adapter. You configure the settings on the team network adapter. Note: network teaming is a good high-availability option for general network connectivity. However, for specific use with ISCSI, you should consider using MPIO for redundancy across multiple network paths instead of network teaming. HBAs. Similar to network adapters, HBAs are made of microchips and physical ports that can be embedded on a motherboard or on an expansion card. However, unlike network adapters, HBAs provide connectivity to a SAN. HBAs are more expensive than network adapters, although they are not the most expensive storage connectivity solution. Fibre channel HBAs are uniquely identified on a fibre channel network by a worldwide name, WWN. A WWN is a configurable 64-bit address that every fibre channel network component uses, although they do not apply to ISCSI HBAs. Note: WWNs are configurable, so relying solely on WWNs is a security risk. Some attacks rely on WWN spoofing, which is the process of using another device's WWN without authorization to gain access to backend storage. For performance, Fibre channel HBAs offer speeds up to 16 Gbps per port, whereas ISCSI HBAs typically offer 1 gigabit per second or 10 Gbps per port. However, you can combine ports to achieve greater performance, which is similar to other storage expansion cards. The industry offers theoretical fibre channel speeds up to 64 gigabits per second currently by allowing you to combine 4 16 Gbps ports. HBAs are load balanced with software, and their speed is based on the total number of ports and optimized paths to the backend storage. In the real world, it is uncommon for a host to have more than 2 paths to a single SAN controller. Instead, companies generally opt to have paths going to more than one SAN controller while using 2 HBAs. The industry has announced that upcoming solutions can meet a new standard of 32 Gbps per port performance. However, with the popularity of Fibre channel over Ethernet and converged networking, Fibre channel and Fibre channel HBAs are beginning to lose market share to Ethernet and converged adapter solutions. Converged network adapters. Converged network adapters are composed of microchips and physical ports, sometimes embedded on a motherboard and other times on an expansion card. You can configure converged network adapters to provide connectivity to an Ethernet network or SAN, or to both. Converged network adapters typically cost a little more than an HBA because they are built with multiport and multi-protocol support. Converged network adapters typically support multiple protocols simultaneously, which makes them the most flexible storage adapter that is available. On the performance side, converged network adapters are capable of achieving the highest speed that a specific protocol can achieve. For example, if one of the ports is an Ethernet port, the converged network adapter can achieve speeds up to 10 gigabits per second. However, because converged network adapters usually provide multiple port types, they typically do not achieve the combined speed of a dedicated single-port solution. Currently, converged network adapters are popular because of their flexibility, and organizations typically use them in modern data centers. InfiniBand host channel adapters. InfiniBand host channel adapters, similar to other storage connectivity cards, are composed of microchips and physical ports, typically on an expansion card. Host channel adapters provide connectivity over an InfiniBand network, and they provide the highest levels of performance available today. This high performance comes at a cost, however, because host channel adapters are the most expensive storage connectivity adapters that are available. Some current host channel adapters operate at up to 56 gigabits per second. InfiniBand provides the lowest latency by having less communication overhead than competing solutions, such as Ethernet. However, organizations use InfiniBand rarely, typically because of high cost, the training that is necessary to use and manage it, and the competitive features of lower-cost solutions. Disk controllers. Disk controllers are microchips that facilitate communication between hard disks and a central processing unit, CPU, over an associated bus. Early versions of disk controllers were embedded on dedicated expansion cards. Today, most disk controllers are embedded in a disk drive. Additionally, with the widespread adoption of virtualization, virtual disk controllers are quite common. Virtual disk controllers sometimes emulate physical disk controllers, although newer virtual controllers are written specifically for virtual implementations, and they do not rely on emulation. Disk controllers have the following characteristics. Most servers offer built-in RAID capabilities and a specialized disk controller or RAID controller, which facilitates the RAID capabilities. Another type of specialized disk controller or array controller facilitates communication between a server and a DS appliance. Physical disk controllers typically operate over a serial ATA, SATA, or serial attached SCSI, SAS interface. Virtual disk controllers typically emulate integrated drive electronics, IDE, or SCSI controllers. In this demonstration, you will see how to add the ISCSI target server role service. Create two ISCSI virtual disks and an ISCSI target. Connect to the ISCSI target. Verify the presence of the ISCSI drive. Demonstration steps. Add the ISCSI target server role service. On LONDC1, use Server Manager to add the ISCSI target server role service in File and Storage Services. Create two ISCSI virtual disks and an ISCSI target. 1. On LONDC1, in Server Manager, in File and Storage Services, browse to ISCSI. 2. Create a new ISCSI virtual disk with the following settings. Name: ISCSI Disk 1. Disk size: 5 GB. ISCSI target: new. Target name: LONDC1. Access servers: 172.16.0.21. 3. Create a second ISCSI virtual disk with the following settings. Name: ISCSI Disk 2. Disk size: 5 GB. ISCSI target: LONDC1. Connect to the ISCSI target. 1. On LONSVR1, open Server Manager, and on the Tools menu, open ISCSI Initiator. 2. In the ISCSI Initiator Properties dialog box, configure the following. Quick Connect, LONDC1. Discover Targets, ICN.1991, 05.com, Microsoft, LON, DC1, LON, DC1, Target. Verify the presence of the ISCSI drive. 1. On LONSVR1, in Server Manager, open Computer Management from the Tools menu. 2. In the Computer Management console, in Disk Management, verify that the two 5 GB ISCSI disks are present. Note: the new disks are added, but they all are currently offline and not formatted. These are listed as Disk 11 and Disk 12. Lesson Overview. Enterprises often require storage features that smaller organizations do not need, and these advanced features typically simplify storage management. An ISNS server is a central directory of ISCSI targets. DCB helps ensure that QoS goals are met on high-speed converged networks that carry multiple types of data. Multipath I/O, MPIO, is used to identify multiple paths through a storage network for redundancy and performance. Objectives. After completing this lesson, you will be able to describe ISNS, describe DCB, describe MPIO, configure MPIO. In complex IT systems, there are many storage devices and many devices that need access to storage. An ISNS server has a database with a collection of information about storage devices and where that storage has been allocated. This database and the associated ISNS protocol make it possible for devices that need storage to find allocated storage devices. That is, ISNS clients query the ISNS server to find storage allocated to them. ISNS is a flexible protocol that uses few system resources. ISNS servers and ISNS clients use the ISNS protocol to interact with one another. Clients can use ISNS to discover ISCSI storage devices automatically, and you can use ISNS to configure and manage ISCSI storage devices. ISNS also facilitates the same operations for fiber channel devices by using an Internet Fiber Channel Protocol gateway. However, because ISNS can perform storage discovery and configuration tasks, you can use ISNS to make an IP network function similar to a SAN. You also can use ISNS to integrate IP and fiber channel networks seamlessly because ISNS can emulate fiber channel fabric services and manage both ISCSI and fiber channel devices. As a result, if ISCSI and fiber channel devices comprise your storage network, this is very valuable to your organization. You can use ISNS to manage groups of devices instead of managing them individually, because after a device is registered in the ISNS database, it no longer requires manual configuration. ISNS serves as a central configuration point by which management stations can configure and manage the storage network. ISNS components. ISNS has three primary components: clients, servers, and a database.
ISNS client.
When an ISNS client attempts to discover a storage device, it initiates communication with ISNS by using the ISNS protocol. ISNS clients are typically processes resident in the storage device. The ISNS client registers device attribute information, downloads information about other registered clients in a discovery domain, and receives asynchronous notification of events that occur in their discovery domain. A management station is a type of ISNS client that has access to discovery domains contained within ISNS. ISNS servers. ISNS servers respond to ISNS protocol queries and requests. ISNS servers also initiate ISNS protocol state change notifications. Authenticated information submitted by a registration request is stored in the ISNS database. ISNS database. ISNS servers use the ISNS database as an information repository. The ISNS database contains information about ISNS client attributes. It is possible to store ISNS client attributes in a lightweight direct access protocol, LDAP, directory by using a directory-enabled implementation of ISNS. ISNS functions. The four main functions of ISNS are: a name service. All entities in a storage network can use this service to register their names and other information in the database. All registered entities can then query the ISNS database to find other entities. A discovery domain and login control service. This service helps to divide storage nodes into groups. These groups are then used for administrative purposes and to control login activities. A state change notification service. The ISNS server uses this service to issue notifications about events on the network. Mapping information to an ISNS database. ISNS maps naming and discovery information about ISCSI and fiber channel devices to an ISNS database. ISNS installation and configuration. The ISNS server service is a Windows feature included in Windows Server. You can install it by adding the feature in Server Manager or by using the Add Windows feature complete. After installation, you can launch the ISNS server from the Tools menu in Server Manager. You can then register ISCSI devices and group them into discovery domains and discovery domain sets. When you are configuring the Windows ISCSI initiator, you specify which ISNS server IP address or domain name system fully qualified domain name, DNSFQDN, to use. The initiator will query it to automatically discover all of the ISCSI targets present, essentially making manual configuration of portals unnecessary for your initiator. To perform ISNS server registration, use the following Windows PowerShell commands, which manage Windows Management Instrumentation, WMI, objects. To add an ISNS server, use the following command. Set my instance namespace root / my class WT _ ISNS server, arguments at server name equals ISNS server name. To view ISNS server settings, use the following command. Get my object namespace root / my class WT _ ISNS server. To delete an ISNS server, use the following command. Get my object namespace root / my class WT _ ISNS server filter. Server name equals ISNS server name. Remove my instance. Most existing data centers typically have several physical networks that accommodate different organizational needs. For example, system administrators and users might use an Ethernet network, data storage might use a separate physical fiber channel network, and high-performance computers might use an InfiniBand network. However, having separate networks increases costs and management overhead when you are building and maintaining the networks. DCB, which was developed by an Institute of Electrical and Electronic Engineers, IEEE 802.1 Working Group, provides a standard by which you can combine these networks into a single physical infrastructure that supports all of the above protocols and ISCSI. Typically, when you use a converged network adapter or a dedicated ISCSI HBA, the adapter vendor's software includes the ability to configure hardware-based QoS and other features of DCB. Additionally, the network switches to which hosts connect must support DCB. Features of DCB include congestion notification. You can use this to manage congestion for protocols that do not have built-in control mechanisms. The congestion notification can help the devices sending data to regulate the traffic that they are generating in order to avoid congestion. Priority-based flow control. This is a link layer flow control mechanism that you can control based on the type of data being transmitted on the network. You can use this feature to target flow control instead of stopping data flow without regard for what is being transmitted. This last practice was a feature of the original Ethernet flow control. To enhance transmission selection. This enables the system to reserve bandwidth for ISCSI and other network protocols. You can use enhanced transmission selection to set aside a specific amount of bandwidth for ISCSI as dictated by your requirements or usage. This helps to increase performance. Data Center Bridging Capabilities Exchange, DCBX, protocol. This enables devices such as the network adapters and switches to communicate and share capabilities and configuration information. Installing and configuring DCB. DCB is a Windows Server feature that you can install from Windows PowerShell or by using Server Manager. To install DCB from Windows PowerShell, open a command prompt, type Install Windows Feature, Data Center Bridging, and then press Enter. Configuring DCB. You use Windows PowerShell to manage the QoS functionality in DCB. The complets are in the NetQoS, DCB-QoS, and NetAdapter modules. To view all complets that relate to DCB-QoS, run the get-help QoS command. Alternately, to retrieve the complets that are available in each module, run the get-command module DCB-QoS, NetAdapter, NetQoS command. MPIO is a storage network enhancement that provides multiple physical paths from a computer to a block storage provider, regardless of whether the storage attaches directly to the storage provider or is available over a network. MPIO has been built into Windows Server since Windows Server 2008 and was available as a separate component for Windows Server 2003. In addition to this support built into Windows Server operating systems, many storage vendors offer their own MPIO software that can be installed on computers running Windows Server that connect to the backend storage. You use MPIO mainly in these situations to create or maintain a highly available storage infrastructure. In this situation, MPIO is combined with other high-availability technologies, such as failover clustering, network load balancing, and data center availability. Data center availability specifically maintains power, cooling, and the network. Microsoft MPIO can handle up to 32 paths to the storage infrastructure to maximize throughput for high-performance requirements. In this situation, MPIO uses MPIO load balancing to maximize the throughput to storage. In most deployments, high availability is still configured so that if a path fails, all traffic uses an alternate path, and throughput drops down to single path levels. MPIO works in parallel with other software. One such piece of software is the Device-Specific Module, DSM. A DSM is a storage vendor software component that facilitates efficient interaction with back-end storage. The DSM software works in conjunction with the MPIO software for initialization events, I/O events, and other aspects of communication to back-end storage. Similar to MPIO, storage vendors and Microsoft each provide their own DSM software. In this demonstration, you will see how to configure MPIO. Demonstration steps. 1. On LON, SVR1, in Server Manager, add the multipath I/O feature. 2. After installation is complete, restart LON, SVR1 and sign in as a datum/administrator with the password pa55w.rd. 3. In Server Manager, on the Tools menu, open MPIO. 4. In MPIO Properties, on the Discover Multipaths tab, add support for ISCSI devices, and then restart when prompted. 5. After restarting, sign in as a datum/administrator with the password pa55w.rd. 6. In Server Manager, open MPIO, and then verify that MSFT 2005 ISCSI bus type _0x9 is listed as a device. Lesson Overview. File sharing is a core service that Windows Server provides. Each new version of Windows Server includes enhanced file sharing capabilities for untraditional scenarios, such as storing virtual machine files on a shared folder instead of a SAN or locally attached storage. You can use Server Manager to create SMB shares for Windows clients or NFS shares for Linux clients. In this lesson, you will learn how to create and manage shared folders. Objectives. After completing this lesson, you will be able to describe the SMB file sharing protocol. You identify configuration options for SMB shares. Configure SMB shares. Describe the NFS file sharing protocol. You identify configuration options for NFS shares. Configure NFS shares. SMB is a client-server file sharing protocol that was created in 1984. Microsoft modified the original SMB and began using the name CIFS in 1996. Today, the terms SMB and CIFS are used interchangeably to refer to the same file sharing protocol. This lesson uses the term SMB to refer to the technology. SMB is on multiple platforms, and an open-source version of SMB, named Samba, is supported on non-Windows platforms and is compatible with SMB. There are multiple versions of SMB, and each new version has additional capabilities and enhancements. The version of SMB is incremented with the release of new operating systems. When two computers use SMB, they negotiate which version to use. If one computer is capable of SMB 2.0 and another is capable of SMB 3.0, then they use SMB 2.0. The following table lists the version of SMB that different Windows operating systems include. Operating System SMB version. Windows 10 and Windows Server SMB 3.1.1. Windows 8.1 and Windows Server 2012 are two SMB 3.0.2. Windows 8 and Windows Server 2012 SMB 3.0. Windows 7 and Windows Server 2008 are two SMB 2.1. Windows Vista and Windows Server 2008 SMB 2.0.2. Previous versions SMB 1.x. Removing SMB 1.x. Current Windows versions do not have any dependencies on SMB 1.x. If your network no longer includes Windows XP or Windows Server 2003, then you should consider disabling SMB 1.x by removing the SMB 1 feature. To ensure that your network does not have devices that are using SMB 1.x, you can enable auditing of SMB 1.x use on your servers. The events are stored in the Microsoft Windows SMB server/audit log. Enable SMB 1.x audit, logging with the following Windows PowerShell command. Set SMB server configuration. Audit SMB 1 access $true. To disable SMB 1.x, use the following Windows PowerShell command. Set SMB server configuration. Enable SMB1 protocol $false. SMB3.x features. Each new SMB version provides additional functionality that supports new features in Windows Server. Some of the most significant enhancements started with the introduction of SMB 3.0, which offers significant performance improvements, including support for storage of SQL Server databases and Hyper-V virtual machines on SMB 3.0 shares. SMB 3.0.2 provided the functionality that enabled you to implement the scale-out file server feature for highly available file shares that store SQL Server databases and Hyper-V virtual machines. Additionally, it enables bandwidth limitations and was the first version to allow you to disable SMB 1.x. SMB 3.1.1 has the following new features. Pre-authentication integrity. Protects from man-in-the-middle attacks by using a secure hash algorithm 512, SHA 512, hash to verify packet contents during session setup. SMB encryption improvements. SMB encryption now defaults to use the AES 128 GCM encryption algorithm that has significantly better performance than AES 128 CCM, which was used in SMB 3.0.2. Cluster dialect fencing. To support rolling upgrades of scale-out file server clusters, file shares in mixed mode use SMB 3.0.2. After all nodes in the cluster are upgraded, then file shares begin using SMB 3.1.1. Additional reading. For more information, refer to what's new in SMB in Windows Server, http://aka.ms/utahq2. The creation and configuration of file shares has long been a core part of network administration. The ability to share files is one of the reasons that computer networks first became popular. Most administrators are aware that you can create shared folders from within File Explorer. However, in Windows Server, you also can create shares by using Server Manager and Windows PowerShell. In Server Manager, the terms file share and SMB refer to the same component. Share and NTFS permissions. The permissions a user has to access files on an SMB share are a combination of share permissions and NTFS permissions. The most restrictive set of permissions always applies. For example, if you give a user full control NTFS permissions, but he or she has only read share permissions, the user's access is read. To simplify data access, when you use the quick profile for creating an SMB share, the share permission is set to everyone full control. Effectively, this means that share permissions are not restricting access to the share, and NTFS permissions are used to control access. SMB share profiles. You can use Server Manager on Windows Server to create a new share. The built-in new share wizard offers 3 SMB file share profiles from which you can choose, including a quick. This is the fastest method of sharing a folder on a network. With this method, you can select a volume or enter a custom path for the shared folder location. You can use the new share wizard to configure additional options, such as access-based enumeration, share caching, encrypted data access, and permissions. You can configure these options and other options manually after you create the share. Advanced. This profile offers the same configuration options as the quick profile and additional options such as folder owners, default data classification, and quotas. To create an advanced profile, you must install the File Server Resource Manager role service on at least one server that you are managing by using Server Manager. Applications. This specialized profile has appropriate settings for Hyper-V, databases, and other server applications. Unlike the quick and advanced profiles, you cannot configure access-based enumeration, share caching, default data classification, or quotas when you are creating an applications profile. The following table identifies the configuration options that are available for each SMB share profile. Share type, access-based enumeration share, caching, encrypted data access, default data classification, quotas, permissions. Quick yes, 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 no, no, yes. Advanced yes, 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 yes. Applications no, no, yes, no, no, yes. Windows PowerShell complets in the SMB share module. The SMB share module for Windows PowerShell contains 35 complets in Windows Server. This includes commonly used complets such as new SMB share, set SMB share, and remove SMB share. If you use the SMB share complets, you can configure any share properties, even those that are not available in Server Manager. If you want to identify the shares that exist on a server and view the properties of those shares, you can use getSMBShare. The default output displays the name, scope name, path, and description. Scope name is only relevant when the server is part of a cluster and displays as asterisk for unclustered file servers. You can use getSMBSession to identify users that are connected to SMB shares. If the users have open files, then you can use getSMBOpenFile to identify open files. If you are concerned about controlling the bandwidth allocated to SMB shares on a server, you can use setSMB bandwidth limit to define a maximum throughput level that is allocated to SMB traffic on a server for different categories. This is useful for Hyper-V hosts to ensure that certain categories of traffic do not overwhelm the host and affect other categories, including default. This refers to all SMB traffic that does not relate to Hyper-V or live migration, such as standard file shares.
Au Hyper-V.
This refers to SMB traffic that you use for running virtual machines, such as accessing virtual hard drives disks on an SMB share. A live migration. This refers to SMB traffic that generates when you perform a live migration from one Hyper-V host to another. Note: to explore all of the cmdlets in the SMB share module, run the getCommand module SMB share command. In this demonstration, you will see how to create an SMB share by using Server Manager. Create an SMB share by using Windows PowerShell. View SMB session information. Demonstration steps. Create an SMB share by using Server Manager. 1. On LON, SVR1, in Server Manager, in File and Storage Services, browse to Shares. 2. Create a new share with the following settings. File Share Profile, SMB Share, Quick, Server, LON, SVR1. Select by volume, D. Share name, Demo Share. Enable access-based enumeration, selected. Permissions, default. Create an SMB share by using Windows PowerShell. 1. At the Windows PowerShell prompt, type the following command, and then press Enter. mkd:/shares/demos_hair2. 2. Type the following command, and then press Enter. New SMB share, name DemoShare2, path d:/shares/demos_hair2, folder enumeration mode access-based. 3. Type the following command, and then press Enter. getSMBShare. 4. Type the following command, and then press Enter. getSMBShare DemoShare FL **. View SMB session information. 1. On LON, DC1, open File Explorer, and then browse to //LON-SVR1 /demoshair. 2. On LON, SVR1. At the Windows PowerShell prompt, type the following command, and then press Enter. getSMB session. 3. Type the following command, and then press Enter. getSMB session, client username adatum \administrator FL **. NFS is a file system protocol, which is based on open standards and allows access to a file system over a network. NFS has been developed actively, and the current version is 4.1. The core releases and characteristics of the NFS protocol are: the NFS version 1. Sun Microsystems developed version 1 in 1984 and used it primarily internally. Initially, NFS was used on Unix operating systems, but was subsequently supported on other operating systems, including Windows. The NFS version 2. Request for Comments, RFC, 1094, NFS, Network File System Protocol Specification, defines version 2. This version focused on improving performance. There is a file size limit of 2 GB because it was a 32-bit implementation. The NFS version 3. RFC 1813, NFS version 3 Protocol Specification, defines version 3, and it introduced support for larger file sizes because it was a 64-bit implementation. It also had performance enhancements, such as better protection from unsafe writes and increased transfer sizes. It also included security enhancements, such as over-the-wire permission checks by the server. NFS version 4. RFC 3530, Network File System, NFS, version 4 Protocol, defines version 4, which provided enhanced security and improved performance. NFS version 4.1. RFC 5661, Network File System, NFS, version 4 minor version 1 protocol, defines version 4.1, which added support for clustering. In Unix, NFS works based on exports. Exports are similar to folder shares in Windows because they are shared Unix file system paths. Microsoft began supporting NFS by introducing the Microsoft Windows NT services for the Unix add-on pack in 1998. The product was used to integrate Windows-based computers with Unix-based computers. One such integration feature was support for NFS. Microsoft continued to develop the product under the original name until 2004 when Microsoft Windows Services for Unix 3.5 was released. At that time, the product was renamed Subsystem for Unix-based Applications, SUA, and the functionality was split as follows. The Unix Utilities and Software Development Kit, SDK, became a free and optional download from the Microsoft Download Center. A portion of SUA, the client for NFS component, and the server for NFS component became Windows features. The SUA feature was deprecated in Windows Server 2012, and it is no longer available in Windows Server. However, client for NFS and server for NFS are still supported and available as Windows features. The two components for NFS support in Windows are client for NFS. This component enables a computer running a Windows operating system to access NFS exports on an NFS server, regardless of which platform the server runs on. Server for NFS. This component enables a Windows-based server to share folders over NFS. Any compatible NFS client can access the folders, regardless of which operating system the client is running. The vast majority of Unix and Linux computers have a built-in NFS client. Support for NFS has been improved and expanded with each iteration of the Windows Server operating system as follows. Windows Server 2008 R2 introduced support for Kerberos version 5, v5, authentication in server for NFS. Kerberos v5 authentication provides authentication before granting access to data. It also uses checksums to ensure that no data tampering has occurred. Windows Server 2012 introduced support for NFS version 4.1. This support included improved performance with the default configuration, native Windows PowerShell support, and faster failovers in clustered deployments.
Usage scénario.
You can use NFS in Windows in many scenarios, and some of the most popular uses include a VMware virtual machine storage. In this scenario, VMware hosts virtual machines on NFS exports. You can use Server for NFS to host the data on a Windows Server 2012 R2 server. Multiple operating system environment. In this scenario, your organization uses a variety of operating systems, including Windows, Linux, and Mac. The Windows File Server system can use Server for NFS and the built-in Windows sharing capabilities to ensure that all of the operating systems can access shared data. Merger or acquisition. In this scenario, two companies are merging. Each company has a different IT infrastructure. Users from one company use Windows 8.1 client computers, and they must access data that the other company's Linux and NFS-based file servers are hosting. You can deploy client for NFS to the client computers to allow the users to access the data. The built-in new Share wizard offers two NFS file share profiles from which you can choose. Creating a quick profile is the fastest way to create an NFS share, but it does not have some of the customizable share options that are available with advanced profiles. After you create a quick profile, you can configure the advanced sharing options manually outside of the new Share wizard. The advanced profile is the most customizable way to create an NFS share. You can use it to set folder owners for access denied assistance, configure default data classification, and to enable quotas. To create an advanced profile, you must install the File Server Resource Manager role service on the file server. Installing NFS on the server. You can install NFS on the server by using Server Manager or Windows PowerShell. When you use Server Manager, you have to add the File and Storage Services role, and then install the Server for NFS role service. To use Windows PowerShell to install NFS on the server, run the following command. Add Windows feature FSNFS service include management tools. Creating an NFS file share. After you install NFS on the server, you can create an NFS file share by using either Server Manager or Windows PowerShell. To create an NFS file share by using Windows PowerShell, Run the following command to configure an NFS file share named share1 for the directory located at d:/shares/share1. New NFS share name share1 path d:/shares/share1. Authentication for an NFS share can use Kerberos v5 authentication or no server authentication. When you use Kerberos v5 authentication, Active Directory Domain Services, ADDS, is used to authenticate the user account. When you use no server authentication, you can map user ID, UID, and group ID, GID, from a Linux system to ADDS accounts to assign permissions. When you configure share permissions for an NFS share, you typically define hosts that are allowed to access the share. To allow all hosts, you can select all machines. You also can allow and deny specify hosts. Best practices. You should consider several best practices before you implement NFS in your environment, including using the latest version of NFS servers and clients. Currently, NFS version 4.1 is the latest version and is supported on Windows Server 2012 and later, and Windows 8 and later. By using the latest version of server and client operating systems, you can take advantage of the latest performance and security improvements, such as client-server negotiation and improved support for clustered servers. Using all available security enhancements. Since NFS version 3.0, NFS has offered Kerberos security options to strengthen NFS communication. You should use the following options when possible.
O Kerberos v5 Authentication Protocol.
This is the recommended authentication protocol to maintain the highest authentication security. O Kerberos v5 Authentication and Integrity. This adds integrity checking by using checksums to ensure that data has not been altered. O Kerberos v5 Authentication and Privacy. This adds encryption to the authentication traffic, not allowing anonymous access. Although anonymous access is an option for NFS shares, you should not use it because it reduces the security of your file sharing environment. NFS module for Windows PowerShell. Since Windows Server 2012, NFS has had its own Windows PowerShell module. To list all of the 42 complets that are available in the module, run the get command module NFS command. Some of the most often used complets from the NFS module are New NFS share. This complet creates an NFS file share. Remove NFS share. This complet removes an NFS file share. Get NFS share. This complet retrieves information about the configuration of an NFS file share. Get NFS share permission. This complet retrieves NFS file share permissions for a share. Get NFS client configuration. This complet retrieves the NFS client configuration settings. Get NFS client group. This complet retrieves the client groups configured on an NFS server. New NFS client group. This complet creates a new client group on an NFS server. Revoke NFS share permission. This complet revokes NFS file share permissions from an NFS file share. Set NFS share. This complet changes the configuration settings of an NFS share. Set NFS client configuration. This complet changes the configuration settings of an NFS client.